Start recording. Okay, so good morning once again, and let me share my screen. Yeah, the screen sharing has been enabled, and we have already discussed. Let me just open the previous discussions quickly, and you will recall what we have already done. So we have already seen the binary search tree, primary operations. Also, we have seen that we are going to have searching, find, min, successor, insertion, deletion. Up to insertion we have covered. Before we proceed further, I would like to share with you some of the sample code so that those who are not so good in programming, they can practice and do this of your own. So first thing, of course, you will require a node to be declared. Here, this field can be data or key, whatever. Left and right pointers, of course, needed. Parent will also be needed, especially during deletion, and useful also during successor. For successor also, it can be a good way to use. Although through stack, etc., you could do, but because it will be frequently needed for many operations, it's always a better option to store a parent. Of course, it adds to some additional memory needed, but because algorithm will work faster and we will be able to immediately use, so it's a good way. Well, in order traversal, nothing difficult. I need not rush. So searching, given the BST, given the data, of course, you can have it iterative while writing a condition. If the data is less than this, of course, I will go on the left side. Otherwise, I will go the right side. So maybe I can have either, maybe I can say I will write current pointer, current equal to BST. It's always better that you take another variable and then you can keep on making current equal to something. You know what to do, else current equal to something. And then finally, you will be ultimately able to reach, and maybe you will return current. If the value is not met, current should become null and I should be able to reach there. And if the value is available, current should stay to that node and then I should be able to do that. So in while loop, I should ensure that if current has become null, unnecessarily current arrow data, etc. values are not applied. So maybe you have to think of doing that in a proper manner. Then finding minimum. Well, I can have again a node star x. Maybe you can write node star x, and then you can start with the BST. Now, ultimately, again, you have to go to the minimum, means ultimately you have to keep on going to the left, 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 left. When to stop? Ultimately, you should know. But if you reach to null, if you say while something not equal to null, when you come out of the loop, you will be on the null value. So null is not the stopping criteria. Probably one step before that you have to stop. Successor. If BST has a right child, effectively this minimum function can be called in the right subtree, assuming the right subtree is right child as the root of that subtree. You can call minimum from that side. It will automatically give you the minimum value. Otherwise, keep on going to the parent. So for going up to the parent, you will need the parent link. As long as node is the parent's right child, how do you compare? You can always say if parents left equal to current node or parents right equal to current node, that also you can compare. Or you can say parents data less than the current node. It means I am effectively the left side. If a parent's data is greater than the current node's data, this means I am the right side. But directly you can compare the addresses. Parents left pointer address versus current node address. If they are same, that will mean I'm the left side. Then comes insertion. So insertion logic is more or less similar to what we did for searching. I can still do the same thing. I will have a current node first time because I might have an empty binary search tree. And if I have empty binary search tree, then I should mean that I'm going to make that node. So if it was if, that means else. So else will mean simply I have got the new node available and BST should become, or root should become that current node. So I have taken PTR data left, PTR to be assigned this, but BST is being assigned this. I have to also make sure that the parent of a PTR is assigned as null in the first case. Why I'm not doing initially? Because sometimes something else has to be given to the PTR. So if the binary search tree is not empty, I will assume that yes, I have to repeat and find the position, find the proper vacant position using current. Of course, keep on traversing, but of course, when you are traversing, you will definitely need now a previous node to be stored somewhere. So I will definitely have a previous node to be stored, previous equal to current, and then keep on doing a previous updation. And then later you can have current arrow left or right equal to PTR. And then in the recording progress, recording enabled. Let me share my screen. Done. Okay, so let's, because of some recording or some Zoom issues, recording was stopped. I'm resuming. So we were talking that while doing insertion, we have this previous node available. So PTR parent to be this and current, I'll say previous is there. So instead of this, I will say now previous node will be needed. So you will be changing your current node. Ultimately, current will become null. So you will be able to store it in some node, let's say previous, and then using that previous, you will be able to do this. Finally, you should know what you have to return and what should be the return type. We have seen why we need return type and no star. Reason is simple. If root was null, then BST root will also change. In that case, changed root should get returned. So for one case, when root was changed BST should be returned. But because we have given return type, for other cases, some return statement will be needed. So the same original BST should still be continued to be returned. Of course, you can also do the same by using here double star. But yes, if you don't know how to call by reference a pointer, so it's an easier way that node star is returned and the same is used. So here you can give a options for having insertion, search, predecessor or successor. So ultimately, successor or predecessor, whichever you want to use. So maybe you can write here that because I'm implementing successor, so I will implement successor, and then I can call that for return to be accordingly called, and then successor to be printed, successor to be used. So accordingly, I can have other cases. And then similarly, I can have all these called. So searching also to be called, insertion, keep on repeating this, and you should be able to get multiple checks by using empty created and then empty insertion, lot of insertions, then searching, one insertion, later deletion also to be done, successor accordingly found, etc., etc. Having said that, let me now just go back and continue with the discussions related to the deletion cases. So we have already seen some of these discussions. Let me now just resume from the deletion cases. So here comes, and let me enable my pen so that I can teach you. Yeah. So now we are going to talk about the deletion requirements. Well, now this is something you have to be careful. So interestingly, deletion probably looks a complex case, but once we are able to simplify, and we will be able to code it easily. Complex case because insertion, we could say we will always reach to the leaf, so not an issue. But a deletion could be of any node needed, any node including root, maybe root also. But that will mean deletion will make the whole structure disturbed. For example, if I have 12, I have 5, I have 3, I have 17, I have 15, I have 20, I have 16, and like that. So similarly, here I have 9, 7, here I have 10, Now assume I want to delete say 12. Well, whole structure is likely to disturb. Say delete 7. What to do? 5. What to do? So for this situations, effectively, if we plan carefully using a divide and conquer policy, we can have effectively all deletions to be easily handled. If we plan properly. Fine. Just start one by one. Which of these nodes you can find to be deleted easily? Yes, you are right. Just imagine if I have to delete 20. Well, situation is simple. Effectively, I have to nothing but make this as a null and free this node. That's it. Why it is simple? Because 20 had no connections. Similarly, same can be for the 16, same can be for the 10, same can be for the 3. So I say that is case 1. Case 1 means delete a leaf node. Now deletion of a leaf node is easy. So by reaching to that node, how will you reach? Say you know the value 20 to be deleted. What you will do? You will apply the search logic. Through search, you will reach to the node 20. Ultimately, this becomes your X. Now X is to be deleted. So you have to ultimately reach to its parent. So X parent, maybe you can say parent, say parent. Sorry. And then parent's left child or right child, whichever this node was, I can easily find out. Accordingly, link that as null. And then that's it. Nothing big to be done. And then free memory, etc. All that to be done. Remember, although 20 has a parent link stored like this, but once 20 will be freed, this pointer will not create a problem. So that's not a big issue. Then think of nodes which are other nodes which you find can be easily deleted. For example, can I delete 7 without much difficulty? Yes. Effectively, I can short circuit something like this. So effectively remove this from this chain and done. What does that mean? Let's say I have here 12, I have here 15, I have here 17, I have here 20, I have here 25. So 25 as a leaf was easy, but if I want to just delete 20, then I can simply say connect like this. But before doing that, I must verify maybe 25 has a left child also. Say it has 23, it has 30, 23 further may have say 22 and 24, but guaranteedly all these values are greater than 20. I want to delete 20. All values are greater than 20. So if I just bypass this and go like this, the whole structure still remains in the similar way. All values are on the right of 17 which are greater than 20 also. So I don't violate any property. Below 25, I have not touched any node, so they also don't violate any property. So I don't get any kind of a disturbance by this. Similarly, let's say I have here 5, say I have here 3, I have here 4. I want to delete 3. As there is nothing this side, I can still say let 3 be freed and 5 be short-circuited to 3's child. Still as a left child because 3 was left child. 3's any value as a part of 3 will be still lesser than 5. So no problem at all. This becomes a case 2. Case 2 means node having a single child. Case 2 means node having single child, not both. So node having single child, again, the deletion will be easy. What I have to do is, say, if I want to delete some node X, ultimately, I have to go to the parent, X arrow parent. Now, its left side or right side will become the existing child, will be equal to the existing child of X. And which side it will go? If X was on the left side, I will have left side. If X was on the right side, I will go have on the right side. And existing child is only one. So whichever child was, the same will become this. Don't forget to connect, say, this existing child. If I assume this is Y, then don't forget that Y's parent should also be updated, because Y's parent is earlier X. Now that should become actually X's parent. Need not write in single line. Why? What I'm saying is, say, X is 3, X is being deleted, and this is Y. Earlier Y's parent is this, but because now X will be freed, Y's parent should become 5. So because this parent link we are not habitual of updating frequently. So you have to do this, because otherwise later during successor, predecessor, or other deletion cases, this might create a problem. Even in insertion also, you might be using parent pointer somewhere. So you have to be careful for that. So case 2 also becomes easy. Then comes the remaining nodes. So remaining nodes effectively will be nothing but we call that as a case 3. And case 3 means the node to be deleted has both children. Node to be deleted has both children. Well, if you have to delete those nodes, then what to do? For example, say here we have 12, here we have 5, here we have 17, 15, say 13, say 17, say 3, say 7. Now, if I say delete 5, or I say 15, or I say 12, all these are case 3, because now I cannot say delete 15 means what? Even if I free this, the tree structure will get disturbed. This node to be connected which side? If I connect to 13, other side is unconnected. If I connect to 17, 13 will be unconnected. Then I have to do so many other permutations. So we avoid all those. We don't go in that complexity. I say, let's do deletion somewhere else. Deletion to be done somewhere at an easy place, at an easy node, and 15 to be replaced by someone. So if I want to delete 15 to be replaced, with whom it should be replaced so that no disturbance comes. Now comes the use of successor or even predecessor also. So I say, if I replace 15 with its successor, the whole BST structure in this side will remain undisturbed. The structure will remain undisturbed. The of BST will remain undisturbed. and that is way it will become easy. So if I have to do that, I can easily say that this 15 will be replaced by a successor. What does that mean? Say I'm talking, this was a 12. Here I have 15. Now I have here 13. I have here 17. 17 might have here 16. 16 might have here, or let's say this was 19. 16 might have here 18. 16 might have something, say this was, let's say 17. This might have further 16. This might have 20. I say 15 to be replaced by its successor. Well, how to find successor? Easy. Say I wanted 15 to be deleted. What I will do? First search for 15. I get this as x. Now x is available as a pointer here. Then I can find out successor of x. Let's say that is called as a y. Obviously, successor will come from the downside, from the child side, because it is guaranteed that x has both children. That is why case 3 is being discussed. And if x has right child existence, successor guaranteedly exists in the right child's minimum value. So I will go to the right child, go to the minimum. Using that successor function, I will reach here. So now what I will say is, after this, I will have, say, temp data equal to y arrow data. And data means full structure I will copy actually, if other fields are also there, because later I will need full structure if other fields exist. Full structure will be copied if other fields exist. Why I am saying? Now I will give a call for a delete effectively y. Well, that's a simple. Delete y is a guaranteedly not going to be case 3. It's a guaranteedly either case 1 or case 2. Why do I say? It's a successor on the right side, on the child side. It means its left child is guaranteedly null because it's a successor and leftmost value. Left child null means it is not going to have 2 children. So either it has a single child or it might be a leaf node. So either it will be case 1 or case 2. So if you call recursively, still it will delete easily. Can be recursive without much of a problem. This can be done. Once node is deleted, then I can say x arrow data equal to temp data. And initially I avoided copying that so that I should not have in the tree 2 values with, or 2 nodes with the same value of 16. If I initially copy instead of 15 here 16, then at present there can be 2 nodes with the value 16. If I don't take care for calling recursively delete correctly, then I again might stuck at the same place. Of course, that can be solved, but yes, simplest can be that I don't copy initially. First, I will delete and then only I will copy. So that can be one way of doing. Even a simpler way can be there, that you can write delete function in a way that you, based on say delete, you have to delete x, you find x, you search for x, and then ultimately you get this. Say you wanted to delete say value, say some value k, and then you searched for value k, and then that becomes x. Now, if X is node of case 1, I will say call delete case 1. Else, if X is a node of case 2, I can decide that easily. Call delete case 2. Else, whatever logic I just wrote, I will find out the successor. I will note down the temp data. And now I will say Y is the successor. If Y is case 1, then call delete case 1 to delete Y. Else, delete case 2, underscore is also there, for Y. And automatically I have all three cases. So delete case 3 is already written here itself, and I can have a separate function for delete case 1, and I can have another separate function for delete case 2. So that way I will be able to implement deletion also without much difficulty. So you can easily see this operation is also going to be order of log n time, because even if you find successor, that will take log n time. After that, deletion will be, this case will be unit time. Maximum to reach to that node. In this case, we have already got the Y pointer. We will be able to do delete and reach up to the leaf node by searching. This also takes log n time. So worst case will mean this log n time plus this log n time. Total still becomes log n. So 2 log n. So still I will say that searching takes log n. And for case 3, successor will be called in case 3. That will also mean that I have log n, order of log n. So total time will be always equal to log. For other 2 cases also in the similar manner. I hope it makes easy and sense to you, and you can easily understand. Try to code this, and once you are able to implement this, I'm sure you will find it very easy, although initially it might look a difficult choice. Let me see if I can show you. Let me just stop sharing for a time being. Okay, so let me just have partial code to be shown to you. If I have the deletion partial code ready with me for discussing with you some partial code for deletion. Yes, I have got that with me. So this is one way, and I can show you the deletion case. Well, so although you can try as per you require, but let me just share with you the corresponding. Let me, I think my meeting is continuing. So let me share screen once again. Yeah. So now you can see the delete. Of course, if I have done type def, struct word will not be needed. If I have not done type def, struct word will be needed. So your choice. But ultimately, I said I will search if I found the value. If I don't find, of course, nothing to be deleted. If the pointer node is a leaf, then it is a case 1. Pointer node is a leaf, that means a case 1. You have to either write a code and then free. If pointer is a single child node, then whether that child was left child, link a parent to the left child, link a parent to the right child. And don't forget that pointer node can be root also. So this you have to take care. Even if it's a single child, and it can be root also. So you have to take care of special situations for considering every time if root gets deleted. Root is leaf, root is single child, root is 2 children. Similarly, then if it has both children, find either successor, like we have discussed most of the code using successor. So you could say, I will replace with a successor. It can be done with a predecessor also. Copy the data in some temporary value, I'll say temp nodes, temp data, and then you can replace this or delete this. And as already discussed, that we can use recursion also, but otherwise I can directly call here. It will be not the case of recursive leading infinite recursion. Either it will be case 1 or case 2. Finally, because the root itself might get updated, so change the root must be returned, and this is how we should do your deletion implementation. Stopping here, let me pause and stop sharing, and let